Hello, everyone, and welcome to the final Australian session of RQI-Online 2020-21. Great title, I love it. Our first speaker today is Joshua Fu from the University of Queensland. So Josh, you want to share your screen? We've got four talks today. And first one is Josh.
Cool.
So whenever you're ready.
Okay, thanks, Nick, for the introduction. Yeah. So I couldn't get Adobe Acrobat to work, so we'll just have to make do with this format. So yeah, as introduced, I'm Josh, and I'm a PhD student at UQ. So as mentioned, the title of my talk is Superposed Unruh DeWitt Detectors. And so before I begin, I just want to acknowledge my supervisors, so Tim and Magdalena. So they always give me tremendous support, and I'd like to acknowledge some collaborators as well. So Caroline and Sho at UQ, as well as Erickson and Rob Mann at Waterloo. So the outline of my talk was as follows. So I'll first introduce the standard model for the Unruh DeWitt detector on a classical path, and then I'll motivate and introduce our model for the detector in a superposition of paths. I'll take everyone on a bit of a whirlwind tour of the different results we've obtained in these different settings and in these various preprints and publications, and then give some future outlook to conclude. So I hope to go really quite quickly rather than sort of stay on a single paper, just because I want to give people a vision and perhaps motivation to look into these detectors in superposition. So if you have any questions or ideas for collaboration, excuse me, feel free to email me at the end or ask a question. So why detectors? So in relativistic QFT, we cannot operationally access the global states of the field. Of course, we can calculate things like correlation functions and Bogoliubov coefficients. But if we want to have some physical basis for these effects and these properties of the field, we really want local measuring instruments to probe these fields in different spacetimes. So a detector is a physical realization of such a probe. It couples locally to the field along some world line in a background space-time, and it can respond to the field via excitations, for example. And this gives operational meaning to the notion of a particle in QFT. So here we've got, say, a detector which is static in Minkowski space-time, and it experiences no excitations, no matter what the frequency of the modes are. But if we accelerate it uniformly in the vacuum, then it sees the field to be populated by thermal particles. And this is a good illustration of the frame-dependent notion of the particle in quantum field theory, and otherwise known as the Unruh effect. So what is the model itself? Well, we typically take this detector to be a point-like two-level system with two internal states, G and E. We interact it with some massless scalar field, but of course this can be extended to more complex fields. And we usually work within the regime of perturbation theory. And this interaction is governed by an interaction Hamiltonian. Eta is your switching function, which mediates the interaction in time. We have our two-level ladder operator, which governs the excitation, de-excitation of the detector, and then some phi, which is a field operator pulled back to a world line, x of tau. We expand our time evolution operator in the usual way and to second order in the coupling strength lambda. And we let the detector and the field interact for some time. So to obtain the detector state, we can trace out the field degrees of freedom, and we obtain a detector state which is just diagonal. And PD is a transition probability, what's commonly interpreted as that. And it's just an integral over the Whiteman functions. And these Whiteman functions are just two-point correlation functions between the field evaluated at some tau and some later time, tau prime. And so just to give a flavor of what a calculation looks like, we can do this for the Unruh effect. So the Whiteman functions have some functional form in Minkowski spacetime. we can substitute our world line, which is this accelerated world line, where kappa is the proper acceleration of the detector, into the Whiteman functions. These are time translation invariant, so they're static, and then we integrate it with respect to tau minus tau prime. And doing this integral, we obtain the response function, which, as you can see, is thermal and is proportional to the Planck distribution with temperature kappa on 2 pi. So the response function is just some normalized transition probability, and I'll use those words sort of interchangeably. And so this shows that this local probe can tell us a lot about the field and its state. We can learn more if we introduce a second detector. So if we have now 2 detectors on these 2 world lines, XA and XB, and they traverse some world line in space-time, then we can again do the same procedure and obtain the detector density matrix, which is now 4 by 4 and has these off-diagonal terms M and L. And these contain non-local correlations between the 2 paths of each detector traverses. And so equation 6 can represent an inseparable state. So of course that means the detectors are entangled. And this can occur even when they just probe the fields locally in space-like regions. And this highlights a property of quantum field theory, namely that the quantum field exhibits these non-local long-range correlations. And so this protocol where we have 2 detectors and they become entangled is called entanglement harvesting. So hopefully we can, I've been able to show that these probes are quite versatile in studying, say, the properties of quantum fields, entanglement properties, and even space-time. So we can put them outside black holes, in anti-de Sitter space. But while the research area is quite active, and there's been a lot of work put into this, most of the studies to date have been limited to classical motion. So Valentina, I think, will talk about another kind of quantum degree of freedom in the motion. But what we're interested in is detectors in superposition. So there are many reasons to study detectors in superposition, but I'll just list 3 for brevity. So the first is quantum communication and thermodynamics. So there's been a lot of work put into studying superpositions of unitary channels acting on like a target system and seeing how it evolves, or seeing how some communication protocol or some computational advantages can be obtained by superposing the temporal order of some gates or some evolution. But to date, a lot of these studies are done within sort of like an abstract process matrix formalism, and we postulate that our detector model can sort of function as like a field theoretic model that realizes some of these studies in a field theory sense. Of course, there's the perennial interest in the intersection of quantum field theory and gravity. And so we, as I'll discuss later, our model gives us the opportunity to study the operational effects of quantum spacetime. So spacetimes with quantized degrees of freedom. And there are, of course, these well-known papers in PRL which study the gravitationally induced entanglement of two superposed masses as they fall in a test chamber. But others have proposed that such setups actually could represent superpositions of space-time metrics. And of course, there are other foundational questions of phenomenology. So Chaslav's group in Vienna have sort of pioneered the work on quantum reference frames. And we asked the question, is a detector in a superposition of paths in such a quantum reference frame? Does it represent some operational approach to describing these reference frames? And so before I move on, I just want to highlight these 2 papers, which were published last year. And so alongside our papers, I think these are the first sort of studies which looked at detectors in superpositions of paths. So the group in Vienna looked at superpositions of accelerations, and Laura's group, Laura and some collaborators looked at quantum switch with detectors. So what is the model itself? So with our original system, we had our detector and field in this product state, but now we can introduce an ancillary or control degree of freedom, which we can obviously prepare in some superposition state. We can take this to be some path degree of freedom, but it could be a polarization, for example. and the detector couples to the field along, say, these n paths via this sum of interaction Hamiltonians. And note that we are sort of free to superpose any of these parameters, like we can superpose the switching time or the word line of the detector. We let the detector evolve along these n paths in a way that's somewhat reminiscent of a path integral, and then we measure it in some superposition basis to obtain the detector field state. So obviously the assumptions that go behind this is that the control can be measured in a superposition state without affecting the detector internal states. So this is something akin to like interfering it back on a beam splitter. And we also assume that the preparation and the measurement of the control doesn't require us to have a common causal past or future in the trajectories. So we don't want to be restrained to study trajectories that just look like a interferometer. So we just assume that any phases that are picked up in this preparation and measurement are just absorbed into the states. So if we trace out the field degrees of freedom, we again obtain a transition probability of the detector. It now contains two contributions. So there are n contributions that a classical detector localized to any one of the paths would feel, sum over them, and then n squared take n non-local terms, which are basically non-local correlations between each of these pairs of trajectories. This non-local term is basically the L term of the bipartite case. And since this non-local term is going to be in general less than the transition probability of a single detector on a classical path, that means the classical detector will have a higher transition probability than a quantum delocalized one. And I just want to point out, if we trace out the control degree of freedom, then we just lose these interference terms, as you might expect. So let's apply our model to some specific cases. As I mentioned, I just want to give a bit of a tour of what we can do with these and give people a sort of sense of what kind of results and what we can learn from these superpositions. So the first thing is to study Rindler trajectories in superposition. So, motivating questions could be, is there such thing as an Unruh effect for superpositions? If we superpose the detector with two proper accelerations, does it experience a superposition of temperatures? These are the three cases we consider. So in this one, the paths are separated by some constant distance. In this one, the paths approach each other and then recede away from each other. And in this case, the differing accelerations, they accelerate in a superposition of different rates. So these are some of our results, which were published in a paper in PID. So on the left, we plotted the transition rate of the detector at various of these three different configurations, and as a function of time and as a function of omega, the energy gap. And we've just plotted the negative energy gaps because it's easier to see what this significant behavior is. So as you can see, for the parallel and anti-parallel cases, the transition rate is effectively static up until some critical point at which the transition rate starts to oscillate very rapidly. And this is really interesting. We associate this point with that in which the paths become causally connected. And as you can see, the rightmost trajectory here is disconnected from the leftmost trajectory up until some point where the light cones overlap. And we see this rapid emission of particles. I should say that negative energy gaps correspond to preparation in the excited state. And interestingly, so this is purely an interference effect. There's no sort of particle exchange going on between the two paths, because we're just working pretty much to first order imperturbation theory. And so, this tells us that the non-local terms can give us information about the causal relationship between these two paths. In this third figure, we've plotted the detector and a superposition of accelerations, and we see that it oscillates in time with roughly two different frequencies as it approaches the horizon and then recedes away from it. So as you can see, none of these transition rate profiles is thermal, so they're all very time dependent. And this is somewhat surprising because, individually, if the detector were localized to one of these paths, it would respond thermally to the field. But we can see that even just from the Whiteman functions, the Whiteman functions depend on the proper time difference, as well as the sum of the proper times, meaning that they are not time translation invariant. And so the correlations encoded in these Whiteman functions leads to a time-dependent transition rate. Interestingly, for the superposition of proper accelerations, we don't get a thermal response either. Thermality is measured by the detailed balance criterion, and the detector doesn't thermalize to either T1, acceleration 1 or acceleration 2 on either of the branches of the superposition. So yeah, we've learned a lot already about what superpositions of paths can tell us, but the next problem we sought to study was the indistinguishability of inertial de Sitter spacetime and thermal Minkowski spacetime. So since the 70s, Hawking and Gibbons, discovered that de Sitter spacetime, because of its cosmological horizon, radiates particles. So a detector in the interacting with the conformally coupled vacuum sees this bath, and therefore the curvature-induced thermality is actually indistinguishable from the thermality induced by just a finite temperature bath in Minkowski spacetime. So to distinguish this sort of global feature of the spacetime, that is curvature, Versteeg and Nick, they introduced a second probe, and they calculated how entangled they become in each setting if they're separated by some constant co-moving distance. And they found that the entanglement between them differs whether you're in the curved spacetime or the flat spacetime. And this shows that this non-local information gives us some access to information about the spacetime itself. And so what we sought to do was just to put the detector, rather than having two detectors, just put a single detector in a superposition of these paths and see what happens. And so a co-moving distance in de Sitter spacetime, at least for inertial trajectories, is where one goes on one of these paths at constant x, and then another detector goes on one of these paths at constant x. So there's a changing Euclidean distance. So the title here is slightly wrong, but on the left here, I've plotted the transition probability of the detector when it interacts with the field with a compact switching function on each of the branches of the superposition. So in the thermal case, this is symmetric. As we fix one of the switching regions on one branch of the superposition and move the other one up and down, we see that there are resonant effects, which are akin to those we saw in Rindler space at the points at which the light cones of the switching regions are causally connected. For the de Sitter case, this is also the case, but since the trajectories are sort of diverging, at the earlier case, this transition probability, this resonance effect is similar to that in the thermal bath, but as we shift one of them later in time, it becomes redshifted or smeared out, essentially. And when the co-moving distance is sufficiently far apart, we actually don't see this resonance effect because they are never in causal contact in the future. So for the transition rate, we see that in the thermal bath, the transition rate is time independent, but non-thermal. So this is very surprising because if you put a detector in an oven, we would expect it to thermalize to the temperature of that oven. Our model predicts that if we superpose it at two locations in that oven, it doesn't thermalize at all. The origin of this effect, we're not sure yet, but it still shows that there's a lot of intriguing physics to be discovered. For the transition rate of the de Sitter superposed detector, we see that in the infinite past, the trajectories are very close together, and so the transition rate is effectively that of a single classical detector. As we move into the future, the trajectories begin to diverge, and there's these oscillations due to the interference between the two paths, and it equilibrates to that of half of a detector as the interference terms vanish. So I want to take a bit of a different tack now. So I've been previously associating this control degree of freedom with the trajectory degrees of freedom of the detector. There's nothing actually constraining us to associate this control subsystem, whatever it may be, to the space-time itself and give the space-time some quantum degrees of freedom. I want to emphasize this is a phenomenological approach. We're not positing how to put the universe in superposition, but we have all the ingredients that we need to calculate observables in this hypothetical quantum space-time. So we can quantize a field on manifold 1 and another field on manifold 2 and calculate the correlations between those fields. But there's not two universes. There's just one universe in a superposition of two different amplitudes. And so while this seems a little bit far-fetched, one could consider, say, the dark energy of the universe as the source of the curvature of our universe, and treating it as some quantum system. If we were to initialize it in some superposition of densities, then conceivably it could cause the universe to expand in a superposition of rates. And so, yeah, other people have also, considered these sort of wild scenarios where we have superpositions of black holes. So in this one by Zurek in Nature Comms, they study a black hole in a superposition of locations and its decoherence due to its interaction with its own radiation. And Magdalena and some colleagues looked at putting a black hole in a superposition of locations and seeing how that induces an entangled temporal order depending on which way a probe system takes, whether it's closer to one of them or the other, because there's some relative redshift depending on where it is. So what we sought to do was superpose de Sitter spacetime. And of course, this is, again, a little bit unusual, but this is obviously a problem that is that faces any theory of quantum gravity. We expect there to be such, quantized degrees of freedom in a spacetime. And so I want to point out that spatial superpositions are fundamentally different to curvature superpositions, for example. So what I mean by this is that a superposition of a classical background is diffeomorphic to the case in which we have a classical background and a probe is in a superposition of classical paths. And so what I mean is this: so we can write our superposition of the state as some, xi world line and xi plus L world line, and these two basis states are related by the unitary transformation, T, we'll just call it. And this means that our state can be written as either a superposition of paths, or it can be written as a single path with some modified superposition time evolution dynamics. And it's quite straightforward to show that the observables between these two perspectives are invariant. And you can also see this preprint by Magdalena on this discussion. Alternatively, so I should say that, yeah, we consider de Sitter spacetime rotated at two different angular rotations, which is equivalent to a detector located at two angular points in the spacetime. But we can also superpose the curvature of the universe. And in this case, we have two different manifolds which are independent solutions to GR. And there's no global coordinate transformation which maps these two metrics onto one. And so there's no sort of equivalent diffeomorphism in this case. There's an analogy with EM, for example, to make this a bit more conceptually easy to understand. If we superpose a charge distribution in two places, then, from the reference frame of the charge, we would sort of expect a distant probe to look like it's in a superposition of locations. But if we were to superpose the charge density to be between like a cube and a sphere, then no such analogy kind of exists, or no coordinate transformation exists. So what we do is we study this for static de Sitter spacetime. We just do this because it's convenient. And so the first thing we did was spatial superpositions, so in which case the detector on the different branches of the superposition experiences an equal redshift. And we see here that the response of the detector is thermal. This is quite surprising because we previously saw that in the thermal bath, the detector doesn't thermalize. So that's a bit of a mystery still. Even more interestingly, the response of the detector is operationally equivalent to the case where a detector is superposed along axes orthogonal to the acceleration of its motion in Minkowski spacetime. So these are operationally indistinguishable according to a probe in these spacetimes. If we put the universe in a superposition, again, we have some time-dependent transition rate. And this is operationally equivalent to a detector traveling in a superposition of proper accelerations in Minkowski spacetime. So on one hand, this is quite an unsurprising result because by the equivalence principle, we know that the effects induced by curvature are somewhat analogous to the effects induced by acceleration. And since static de Sitter spacetime is conformally related to Rindler spacetime, this is, perhaps expected. The surprising thing is that quantum states of spacetime are analogous to flat spacetime trajectory superposition at all. So on the latter side, we have a fairly innocuous semi-classical problem. But on the former, some people would sort of question whether even quantum states of spacetime can exist at all. So this is an interesting research direction to pursue in the future. There's still remaining questions of whether we can superpose de Sitter spacetime with Schwarzschild spacetime, for example, and whether there's some super selection of rules. Oops. Okay, I don't know why I clicked there, but I presume I have 5 minutes left. So yeah, just before I wrap up, I'm just going to give a brief tour of entanglement harvesting because that's of course all the rage at the moment. So we have our detector density matrix with 2 detectors. And we have a spatial superposition. The M term is the same in both cases, but the P term in the density matrix is less in the quantum case. This is important because the concurrence is a competition between the M and the P terms. And we can also consider temporal superpositions in which both detectors are switched on in the past, or both detectors are switched on in the future, or one in the past, one in the future, and vice versa. And Laura studies this in Minkowski spacetime in the paper I mentioned before. So these are some of the results. I won't go to the liberty of explaining them all, but I'll point out these 2 in particular. So in this one, we've studied entanglement harvesting for superposed detectors in a temporal superposition in de Sitter spacetime. And just let me check the chat in case. Okay, is the picture out of focus for the others?
Yeah, it's the quality's really bad.
Okay.
Stop sharing screen and share again. That would help.
Okay, sorry. I'll try that again. I think probably the internet is.
It didn't help really. So maybe try switching off your video, perhaps.
Okay. Yeah, I'll try that.
Especially if you're almost done.
Yeah. Somewhat better. No. I'll just keep going. Yeah, you can find these at the paper anyway. So in this case, I'll just zoom in then. So in this case, we have a detector superposed temporally in the cause-effect superposition, and we see that when the detector has some temporal indefiniteness in its switching time, we see that the entanglement is amplified for certain switching times, and then when it is in general amplified over and against the classical detector, which just switches on once in a classical sense. In this picture here, we have the detector in the thermal bath, and this is the temperature of the bath on the x-axis and the entanglement on the y-axis. And as you can see, for certain separations of the superposition, the entanglement can actually grow with the temperature of the field. And this is an interesting result because it sort of goes against a no-go theorem derived by Eduardo and Peter, which showed that entanglement can only decrease with the temperature of the field for 2 detectors. But of course, they didn't account for superpositions of detectors, so we're sort of cheating a little bit. The reason why it increases is because both the M terms in the detector density matrix and the P terms increase. But because the P terms are suppressed by the interference between the trajectories, this causes the non-local correlations to sort of exceed and increase at a faster rate than the transition probabilities. Okay. And so just to conclude, I'll summarize some future directions that we have for our project. I'm still sharing, yeah. So yeah, we want to study detectors and superposition in ADS. So I've already, so Laura again has found that there's this sort of anti-Unruh phenomena in ADS, in which case the detector's response decreases as the temperature of the field increases, a very counterintuitive result, which the origin hasn't really been pinpointed. And so we sought to ask the question, is this in fact enhanced when we put a detector in superposition? And in fact it is. So Laura found this effect to manifest for certain boundary conditions satisfied by the field at infinity. And we found that if we superpose the detector, then it actually manifests for all boundary conditions. So the response eventually starts to decrease as the temperature of the field increases. The next thing we sought to do was to study the detector in a superposition of a black hole, outside of black hole spacetime, for example. And this would sort of be the holy grail of my PhD. So there are a lot of different directions we can study. For example, the gravitational quantum switch, in which case, if we were to superpose the detector at 2 different radii outside a black hole, it would experience different redshifts on each of the amplitudes of the superposition, and this would induce some indefinite temporal order in its switching time with the field. If we perform an entanglement harvesting protocol, then this would lead to some interesting effects and could be called some entangled temporal order of the 2 detectors. We can obviously study decoherence of black hole superpositions, superpositions of masses. I don't really know what that'll yield, but the possibilities are endless. So I mentioned before the question of whether we can superpose de Sitter spacetime with Schwarzschild spacetime. I'm not really sure about that, but I think I'm fairly confident that we can superpose Minkowski spacetime with Schwarzschild spacetime. And that's because there's this, this metric, which is a hollow shell, in which case the detector can be put inside and outside the shell. The shell is flat on the inside and the metric is Schwarzschild on the outside. And in our interpretation, the detector would sort of feel this superposition of metrics. And I have no idea what would happen. But yeah, that seems like a very interesting future direction to pursue. And so as a short tour of this talk, I've talked about classically localized Unit detectors and their applications. I've introduced this control degree of freedom, which allows us to superpose the detector at different locations or different switching times. I've then given a bit of a tour of the settings we can try this this model in: Rindler, inertial de Sitter, thermal Minkowski, Schrodinger's cat for curvature and the space-time, as well as entanglement harvesting as well. So yeah, thank you for listening and tuning in. I'm sorry for the technical difficulties. It's obviously hard to keep track of these things when you're in the midst of it, but yeah, I welcome any questions now.
That's great. Thanks, thanks, Josh. Very nice talk. Let me clap. You can also clap like this. Yeah, you can probably turn your video on again if you'd like.
Sure.
To answer a question. Oh, you don't have to stop. Anyway.
Yeah.
So there are a couple questions in the chat. So let's start with Sandeep. So Sandeep writes, as you mentioned, the superposition thermalizes. As you mentioned, the superposition thermalizes. So is the temperature detected an average temperature between the two different superposed trajectories?
No. Well, we measure. Well, we define in field theory thermalization as the satisfaction of this detail balance criterion, in which case your ratio of your transition rates equals this, I think it's Boltzmann factor with the temperature of the field in the exponent. And so as you can see, like if you take your ratio of these two transition rates, you just get this term, which has an interference term, as well as the local terms at temperature 1 and temperature 2. So this, you know, obviously never equals this basically. So it means that it doesn't actually thermalize at all. Yeah.
Okay, great. So we'll take Edu's question and then Akim's.
Yeah, all right. So nice talk. I was had several questions. I'll try to be brief. So in one case that surprised me is when you consider the superposition inside an oven, right? I mean, constant temperature, and you find that it doesn't thermalize. Do you have more insight on that, or it's just that you check detail balance and it doesn't satisfy detail balance, and that's what you claim?
Yeah. That's pretty much all I can say. You know, we thought that maybe in the accelerated cases, the detector doesn't thermalize because the paths are not like symmetric in terms of their causal connections. That leaves a time-dependent rate. But in this case, you know, there's just two paths, and you know, this is sort of invariant wherever you superpose them. And it's even more surprising, especially since the detectors in superposition in the de Sitter case thermalizes. So yeah, we just checked the detail balance and it didn't.
I don't know. It's funny. I mean, it's also true that if you were to have a detector based mirrored, just one detector, single path, but used mirrored in a particular frame, you're gonna get that doesn't thermalize either in the detail balance kind of condition. Right. So maybe it's related to that, but then again, you get it in de Sitter, so that confuses me a bit. Yeah. Yeah, I don't know. There's also another question. When you consider in all the cases that you consider two detectors, do both detectors have the same proper time in all the cases that you consider?
In the entanglement harvesting?
Yep.
With two detectors? Yes. So we consider the case in which, yeah, the detectors in de Sitter space-time, yeah, they're just separated. They have equal, yeah, redshifts, yeah.
Oh, okay, yeah, that's because I didn't see in your Hamiltonians any redshift factors or anything. So that
Yeah,
is, that can only work if they have the same proper time. That's why I was asking. Yeah.
Yeah.
All right, cool. Yeah, that's it for now. Yeah.
Okay, so let's go to Akim and then Laura.
Right. I don't know, maybe I'm anticipating what Laura might want to say. Yes, so very nicely presented. I think there ought to be a deep link to the next talk by Valentina, which is on work with Laura and with Nick and with Nadine, because what we did there was considering the quantum delocalization of the detector in kind of the Schrödinger or Heisenberg picture. But if you look at this in the Feynman picture, then you have a superposition of classical paths, a coherent superposition of classical paths, which is the same thing as saying that the Schrödinger wave packet is propagating, right? And you seem to be picking out particular classical paths in superposition. So what I'm wondering is, would you agree that if you considered all paths and summed over all of them, you would basically get the scenario that Nick, Valentina, Nadine, and Laura and I considered?
Yeah, it's always been at the back of my mind because I'm very aware of your works, and I have it's always been I've always wanted to ask the question, if we just extend this to the continuum limit or something and put some sort of Gaussian weighting, what would we get? And I think it would be much more complicated. Oh, well, maybe in a sense it would be a simpler calculation, because you just repeat, you just add up all these contributions, which are basically the same between all these paths. I guess as you extend out the number of paths in the superposition, the local contributions, there's more and more interference terms between the paths, and there's only linearly increasing number of local contributions. So I suspect that the detector would just sort of stop clicking at all. It would just decay, because these non-local correlations decay faster, or decay with distance, and then you're only increasing linearly the number of paths, but you're increasing polynomially the number of interference terms, I guess. So I don't know, that's just one thought that I've had. Yeah.
Right, but fundamentally, remember that whenever you want to talk about the classical trajectory, it is really quantum, and you must have some extra thing that keeps it on a quasi-classical trajectory, like a very large mass or something like that. So ultimately, there always ought to be some description of what you do. In the Schrödinger picture, for example, where you have wave packets that travel this way and that way, and in coherent superposition, right?
Right.
I want to make sure we get to Laura.
Trajectories are always fundamentally quantum, but maybe Valentina, will answer some questions in her talk.
Oh, okay. Yeah, thanks.
I want to make sure we get to Laura's question, but Josh, do you want to respond to that real quick?
I'm not entirely clear on the question itself, I guess, or I think perhaps this is a limiting case of the continuous wave packet that coherently is in some wave packet. Yeah, so I'm not really sure.
Yeah, exactly. Yours must be a limiting case of very
okay. I agree. Yeah.
Right.
So Laura.
Okay. First of all, that was a fantastic talk. I've been sort of wondering about some of these questions, knocking around in the back of my head, and just seeing all of this work you did on that is just amazing. I just have sort of one question. I know you mentioned it in passing. Did you find that when you look at those sort of non-local, those non-local contributions to your transition probability between the different branches, do those always decrease the transition probability? Or do they sometimes conspire to actually increase it?
I don't think in my explorations I've found a case in which they conspire to increase the probability, but obviously I haven't proven anything that they must be less than the local terms. So yeah, that'll be interesting to look at.
Okay, I was just curious. And then I guess to answer the other question, I was briefly looking into sort of comparisons between the superposition of position and what Valentina will talk about in the future. So if anyone wants to talk in more detail, we should.
Awesome. Great.
All right, well, that was a great talk and great question time. So let's thank Josh once again.
Everyone.
All right. I do miss the applause, like actual audible applause. And anyway. Okay, great. So next up is Valentina Bacchetti from RMIT.
Hello, everyone. Let me see how I can do this now. While I'm doing that, I want to thank the organizers for organizing this series of talks. And okay, now I think I can share it. Can you guys see my talk? Oh,
Yep,
good.
that's
Okay.
good. Yep.
Cool. Yes, I'm gonna do a preview so you guys can see my what I'm pointing. So keynote. Yes. So yeah. So we're saying I would like to thank the organizers for setting up this series of talks and trying to keep together the RQI community in this crazy year. And yeah, so today I'm going to talk about vacuum entanglement harvesting with delocalized matter. And yeah, before I start with the science, because I'm sort of broadcasting from Australia, I like to do an acknowledgement to the country. And this is something that we do here to pay respect to the custodian of the land. So because I'm in the Dandenongs near Melbourne, I like to acknowledge the custodians of this land, the Wurundjeri people and their elders past and present. And I acknowledge and respect their continuing culture and the contribution they make to the life of the city and this region. Okay, cool. So now starting with the science, as Akim has mentioned, Nick has mentioned, Laura and so on. This is what we have been doing in the past year or so between Nick, Laura, Nadine, and Akim. This is a screenshot that we took during one of our Skype conversations, and I just thought it would be fun to put it out there. And yeah, this is the paper that came out. I think we put it out last year on the archive and got published for Christmas. So it was a very nice present for us. And yeah, I'm actually curious to see the parallel with what Josh just said, and maybe at the end, after I present the results, we can try and draw some parallels and see how the two things can be connected. And before going into the details of what we have done, what I would like to do is actually talk about the motivations, like why we are doing that. I know that we are all like in the RQI community, but I always find like it's very interesting to understand the background of what we're doing, what we're doing. So what we're doing is pretty clear from the title. We are using coherently delocalized already with detectors, as Nadine and Akim proposed in one of their articles a couple of years ago, to try and see, harvest entanglement from the vacuum. We also experiment with trying to do it in a medium, but probably I'm not going to have time to go through the talk. And the idea is to try to understand how the quantum degrees of freedom of the center of mass actually impact the ability of harvesting entanglement. If they enhance it, if they decrease it, and so on. And the motivation for this can be understood through a brief historical recap, and the fact that, as Josh mentioned at the beginning of his talk, is that entanglement harvesting could be seen as a resource. So it's a way sort of as a probe and so on. So as a way of actually doing like measuring things, even if on a qualitative basis. And the reason is because it's, as we all know, like it's very sensitive to the topology, the state of motion, the topology of the space that we use, the state of motion, the boundary conditions of the field. So there's a difference between the quantum vacuum, the medium, and so on. And because of the sensitivity, I think Edu and others have proposed that this could actually be used, for instance, in quantum information. So one can create resources. It could be using quantum information to what is called entanglement metrology, for instance. So quantum seismology has also been proposed. I have no idea how, but I found it pretty cool that that's been like proposed there. So the idea is that, as Josh mentioned as well, like these are very good ways. These are very good tools that one can use as probes to have an operational approach to physics. So one does a measure and you say, okay, I have a set of measures, so now I can sort of give an explanation of the physics and it is underlying. And so for this reason, what one would like to do is to, when one develops the mathematical modeling for these detectors, is to capture as many relevant characteristics as possible and also in the right way, and also be sure that this sort of like cover what an atom, an ion, and molecule would see. So try to make like as physically relevant as possible. And the reason for this is that if we briefly go through just the detectors, is that simple level system, simple in quotes, that it's there to mimic the light matter interaction. It's being proposed by Rindler for this purpose. And what we see is that we have a switching function that we can decide to be in whatever way we want, and also like a smearing function or smearing profile that again we can associate a Gaussian and deltas and so on. Like if it's a delta, it's a point like the detectors. If it's a Gaussian, as a spatial width and so on. And the purpose is in the name. It's just say it describes the spatial profile of the detector itself. And so one legitimate question could be like, is it the spatial width of the center of mass, of the electron degrees of freedom, and so on? Is it right the way we're modeling or not? But the most important part is that, as you guys have shown in plenty of papers, is that entanglement hypersync is very sensitive to the detector's configuration. So I think in one paper of Edu, there's plenty of evidence that, like, depending on how we select the switching function, well, also other papers, or the smearing profile, results are quite different. So one needs to be careful on how to define those parameters in the problem. And for this reason, like, I think it's really important to make this model as experimentally relevant as possible. And so, as we know, like so far, or at least until a couple of years ago, ways this could be done. For instance, I'm just listing 2 cases, or well, 3, but the cases that we are considering is that it all started with saying, okay, let's consider a point-like detector. But in general, these atoms have a spatial, it's a final, they're finite, they're not like point-like. And so like one introduces smearing profile, as I said, as for instance, one consider a Gaussian. And this is all classical. But a possible way to try and sort of include or describe these atoms more as they are experimentally is to introduce quantum degrees of freedom in the center of mass. And so associating a wave function, so something that evolves in times and delocalized, a quantum evolves in time. And so before I go into the details of the model that Nadine and I can propose and that we have used, the first thing that I'm going to do is define a baseline, just because we want to see again the negativity and the possibility of entanglement harvesting in the classical case. And so what we have done is like we have considered the usual initial states where the system, like the 2 detectors are both in the ground states. I don't know if, yeah, I guess you can see my pointer here, and you have the 2 detectors that are separated by distance s, and as usual, they evolve with an interaction that is of this kind. And we have used a Gaussian smearing profile, and we've used a switching function that has compact support, meaning that is switching on and off. So what we are doing, so we have the two detectors don't interact, we're switching them on, they interact, we're switching them off, and we want to check what the negativity is doing after that. And the reason why we consider that specific switching function will become clearer later on, but we are considering it that way so we can compare it with the quantum case. I'll give you an explanation, probably in 10 slides or so. And so, as you guys well know, the procedure that one follows is that we go to second order of perturbation theory. We trace off the field's degrees of freedom, how we have the density, like the state after the interaction at time t. And what we have found is that when we plot the negativity in terms of detector separation, so the distance between the centers of mass and the width, so if we consider a point-like detector or a spatially smeared one with a Gaussian one, this is what we find. And so the reason why we've done is that, so now we have baseline, we have a comparison, we have a baseline that we can use to compare what we're gonna find next with what has been done so far. And so, as I said, the step to try to make these detectors like as similar to what one would see like in an atom or cell is to introduce the quantum degrees of freedom for the center of mass. And as I briefly mentioned before, we have used the model that Nadine and Akim developed a couple of years ago, probably more, where they basically associate wave function to the center of mass that evolves in a specific way. And we're going to see it in a second. So in their case, what they have considered is that the internal degrees of freedom were excited, and so they were, I think, correct me guys if I'm wrong, I try to understand the possibility of emission when the center of mass delocalizes. So in our case, instead, what we have considered is that, so the initial state, everything is like the external degrees of freedom and the field, of course, are in the ground state. So we are in the vacuum. But as I said, as I mentioned, now we have some quantum degrees of freedom from the center of mass. So we have some states that evolve using the Schrödinger equation, as Hakim mentioned in the comment. And this is quite relevant. It's something we need to take into account because it puts some constraints on the velocities of the center of mass. And so, as per before, what we're doing is evolving the states using this interaction Hamiltonian, where now the difference with the previous case is that the field, the field operator now takes as an argument an operator. So we have that X and P are position and three momentum operators now. And so a possible way of defining this relation is through the a spectral theorem of functional analysis that becomes a functional, it's not a function anymore. And we can do that through this operator P that is defined, as you guys can see it here, down at bottom. And this is something that, Hakim and Nadine defined before, but we are using in our, well, it has been defined before, but they're using in the model and we are using in our toy model as well. So the center of mass states can be defined either as a wave function in functions in the position representation, the momentum representation. We're going to use the momentum representation, which is just a way to tell you how one can can do it. And the whole procedure to get to the state at time t prime, whatever, at the end of the interaction, is that we again, we trace out the field, but we also trace out the center of mass degrees of freedom. And so we can get the density matrix for that tells us the correlation, the possible quantum or classical correlations between the internal degrees of freedom, not the center of mass. Again, this is the representation at the second order, where now we get that the excitation probabilities, yes, the excitation probabilities and the entangling terms. So the excitation probability PJ, they depend only on the momentum probability distribution, while the entangling terms depend on the phases terms here, where basically they carry the information regarding where the positions on the center of mass are. So we sort of expecting that we know that these things are non-local, but we need to remember now the centers of mass are quantum as well. So this thing is highly non-local, and as I say in this slide, so they depend on both. They depend on the spatial. So the entangling terms, they are non-local, and they depend on the positions of two centers of mass, and so they depend on the properties of both detectors, while the excitations don't. And this is important because it helps us understanding the behavior later on, the behavior of what we find. So in order to be able to make a little bit of prediction regarding the negativity, there is what we have done, we have taken specific wave functions and switching functions and so on. So for the center of mass to be able to do a comparison with the smeared case, we have taken like the wave functions to be a Gaussian like this kind, and we also have assumed that the two detectors have the same energy gap, the same wave function, the same mass, and so on. So therefore, the excitation probabilities are the same. So one thing that I forgot to mention is that, yes, we have assumed that M, big M, they probably have seen one of the previous slides. It's the mass of both the detectors, and it's the same. So we can basically say the following, that the excitation probabilities are the same in the case that we have considered. Therefore, the formula for the negativity, because I mean, we are tracing out the center of mass degrees of freedom, and the phi also the system is a bipartite one, and so we decided to use the negativity as well. So as in the previous case, what we have here is that in order to get a negativity that is not zero, we need to have the entangling terms are much more prevalent than the excitation, the local, the probability excitation one. So the other thing that we have considered is that, and here comes the explanation of why we want to get a switching function with compact support, and why we're choosing the one that we've chosen. They are reported here. So the reason that, so at the top here, we have the wave function for the center of mass, and in the free time evolution, the wave packet, what happens that in time t minus infinity, t plus infinity, the center of mass wave function is basically completely spread, while at t equals 0, it's localized, or at least as localized as possible. There's still a little bit of delocalization at L. And therefore, we want the interaction to start when the wave packet is localized at t equals 0. I don't know, I hope the slide gives you an idea of why we mean that. And so we want the interaction switch on in that precise moment, switch off later on. And the other thing that as I mentioned before, is that because the center of mass follows the Schrodinger equation, so it evolves using the Schrodinger equation that is non-relativistic, we need to be very careful when, after switching on the interaction, so there is a center of mass recoil, those virtual velocities need to be non-relativistic. So, and this is the condition that we put here. So we said like at most 1% of the speed of light. And because of the momentum probability distribution that we have, like the wave function that we have picked, like a Gaussian, we can say that we can make this assumption. So we say like, okay, we assume that a 3.5 standard deviation, the value of the average value of the momentum is 1 over L. So we can find this boundary here that tells us that in all our calculations, we need to take into account these relations. So the relation between the initial delocalization of the detector, the mass of the detectors, and C. So their product needs to be greater than 3.52 times 100 or 10 to the 2. So, and this is just a way of saying, oh, we need to respect like the fact that we I'm not in a relativistic setting. Okay, sorry, I'm checking the chat to see if there are questions, if you guys telling me that you can't see my slides. Awesome, let's move forward. So we have done these assumptions. So before checking the negativity and so on, what we have done is try and understand what happens to the local probability excitations, and in the next slide to see what happens to the entangling term. So here we have plotted the probability excitations as a function of the detector mass. So we see that the detector mass increases as we go this way, and different colors have different energy gaps, and the dashed lines here are the comparison with the on-route wave detector, the point-like on-route wave detector. And it's pretty clear to see, just like first sight, is that the excitation probabilities decrease both when the energy gaps increase. So this is high energy gap, small energy gap. So you can see it on the trend, and also as the mass decreases. And let me see if I can explain this. So we think that the reason, well, intuitive explanation is that when you switch on the interaction, what happens is that you're basically breaking time invariant. So you're basically introducing some energy in the system, and that energy can go now like either in the center of mass recoil or creating an excitation. And so when the mass increases, basically what happens is that most of the energy will not go to try and make the center of mass recoil, but it will go in creating an excitation. While if the mass is really small, what happens is that part of the energy can actually go in making the center of mass recoil, and therefore we see this sort of behavior. Okay, so we see this decreasing in terms of the detector mass. Well, for the local entangling, we see the following, sorry, not the local, the entangling term, this is non-local. What we see that has the, we plotted it in terms of the separation between the centers of mass. And what we see is that at the center, as the separation between the centers of mass increases, the entangling term seems to be goes to 0. And one explanation there with, and again, the dashed line, as it says here, as a comparison to the point-like on-route wave detectors. The reason for this seems to be that the more separated the detectors are, the bigger the distance, like introducing sort of a length cutoff, and therefore it's harder to create this sort of non-local excitations. So that's the idea. But again, it seems like M seems to be dampened down for these cases. So it seems like this can actually impact the negativity. Before going into the measure of the negativities though, because it seems like at least, well, we need to compare the two terms, but it seems like there is basically very little entanglement between the two detectors, or the external degrees of freedom. What we have done is, okay, let's see what happens if we try to recover classical Uno-Dewey detector. Maybe we can understand this behavior better. We can take in limits. It's a good way to understand, like, if what one is doing is correct, but it's also a way of understanding what's going on in terms of physics. And it helps giving like explanation on if the mathematical model is actually recovering the physics as well, or which part of the physics. So the first idea could be like, okay, if I want to go back to the classical case, what I just do, I take the mass of the detector that goes to infinity, so the detector basically cannot delocalize, it becomes classical. Still maintaining the initial delocalization fixed and maintaining the limit that the velocity of the center of mass needs to be much less than the speed of light. And for the limit, this is definitely clear. But what we have found is that the excitation probabilities tend to go to the point like the limit goes to the point like detector wants. So 0 is just to say the point light, while the entanglement term becomes equal to the one for a smearing function that is a Gaussian for two classical detectors with a smearing function that is classical. So this is telling us that the negativity that we have obtained doesn't. It's neither the one for point light detectors, neither the one nor the one for smeared one. And an intuitive explanation that we found is that the probability excitation, as we said, are local. So they are not affected by the position of the detectors and like and the shape. So we go back to the point like Uno-Dewey detector, while M does depend on the position of the detectors. And therefore, if we make like the quantum probability into a classical one, it now become just a classical probability distribution for the position, we get back into the case where the entanglement terms are smeared. And so we found that we need to be a little bit more careful with taking the limit. So the idea is that we can at least try to see if we can go back to the point-like detector, because if we send the width of the position wave function to 0, we're basically recovering a delta. So we should be able to at least recover a point like your Uno-Dewey detector. And so the way we take these limits is like it's defining a regularization parameter gamma that goes to 0, so that you know, M goes to infinity in the proper way, and capital L does the same, still maintaining this inequality that now becomes this one that, guys, you can see on the slide. And so what we have done, and here we can see also some of the results regarding the negativity for this delocalized detectors. Okay, not yet. What we have found is that, yes, we recover the excitation probabilities and the entanglement terms for the point like Uno-Dewey detector that is classical. And you can see as 1 over LMC goes to 0, like they are identical. But the best way to see this is to the graph and to this plot that we plotted. And so the two arrows, the two red arrows, are just saying that gamma goes to 0, left to right, top to bottom. And basically what we're doing here, as you guys can see, we are increasing the mass, like going from here, here, while at the same time, the separation, like not the separation, that's the initial quantum delocalization is getting smaller and smaller and smaller. And one thing that we have noticed that it seems that for quantum delocalized detectors, at least in our settings, there's no entanglement, like the entanglement harvesting is highly suppressed. And we're going to discuss this in a second, trying to understand why. But as we go into the limit of classical point-like Uno-Debye detector, so if we take the limit, it seems like the negativity is present again. And this is, sorry, the final limit that we found is that if we take incredibly big mass, quite small initial delocalization, we almost recover. This is the same plot that I put at the beginning. We also, that's why I said it was a baseline. We basically, like, we are getting to the past to recover the result for a point like Uno-Debye detector. Okay. So I think I'm almost done. So my time is almost out as well. What have we learned? So for this toy model that we used, it seems that from the plot that I showed here, sorry, 2 slides before this one, the first, it seems like entanglement harvesting is highly suppressed, and at least the entanglement harvesting between the internal degrees of freedom. Okay, and we also managed to see that we can recover the entanglement harvesting for point-like Uno-Debye detectors, taking into account specific limits, but we don't seem to be able, at least for this toy model, to recover the result for a gaseous smear detector. And this is something that sort of agrees to what has already been pointed out, for instance, in this paper by Eduardo, and I don't remember his name, apologies about that. That and also in the paper by Hakim and Dean, that it seems that the spatial smearing profile seems to be more adapt to describe the spatial width, like of the internal degrees of freedom more than the center of mass. But and the reason why, and this is the reason why I stressed first step. The possible reason why we are not seeing any entanglement could be that, so we are focused just on internal degrees of freedom, but there could be entanglement in the center of mass, and this is something that we would like to investigate in the future. But also, this is something that I think has been pointed out by Edu during Laura and Nadim's defense, is that basically, to be able to recover the light matter interaction, the Hamiltonian that we have used is not enough. So there needs to be an extra term that couples the internal degree of freedom and the external degrees of freedom. And it's I think it's in this paper, and that could be one of the reasons why we don't see the entanglement. I haven't thought about it properly, so I don't have the answer. So what to do next? What to do next is probably explore what happens in this case to entanglement harvesting, and trying to understand like how the entanglement is distributed among the degrees of freedom, but also understand which are the degrees of freedom we need to add. And maybe this is something that we can discuss. And now that I have seen Josh's presentation, maybe understand like if there is, how the two representations are connected, like in terms of Feynman diagram or more of a classical representation, how they are connected, and or superposition. Apologies. And yeah, I am done. And this is the paper if you guys want to read it, if you haven't seen it. So thank you. Maybe I stop sharing.
You can still share. That's fine.
Okay. Okay.
Very nice. Oops, I shouldn't be raising my hand. I should be clapping. There we go. Excellent. Okay, so Edu has some questions, he says. So let's go to Edu.
Okay, I'm not sure who was first as well. Okay, I can go. Thank you, Valentina. Very nice talk. Very nice talk. I have I guess a couple of questions. One about the last thing you mentioned. Yeah, that term will definitely have an effect. So the missing term, which is the one that appears because you don't get the dipole approximation only when you delocalize center of mass. You have the Röntgen term, right?
Okay. Yep.
That will harvesting. I cannot tell if it will recover the previous behavior or not because I have no idea. But it's certainly interesting to look at. I was wondering two things. One is in this graphs. I mean, I asked Nadine already about this, but maybe you know more because time has passed, and Laura was also looking into it as well. What is there any separation here that I could call at least approximately space-like separated? Meaning, like, it'd be nice to have a light cone or something like a light cone boundary here, because when we're light connected, right, it could be creation of correlations, not just harvesting itself. If it's space-like, we know it's exactly harvesting. I wonder if you know, you can tell me more about that. If I were to place some light cone here on these plots, where would it lie?
Okay, let me try to understand, because I have to say that probably Laura and Nadine already gave you like a much better answer than I can give you. So I think in our case, the problem is with the switching function that we have considered. If I remember it correctly, like I think there's no possibility of, guys, correct me if I'm wrong. I think Laura and Akim and Nick, but it's a problem of the switching function that we have considered. So I think what's going to happen is that it's I think it's not possible to harvesting entanglement outside of your light cone, but it's more of a problem of the switching function than it is of the
yeah, I mean,
then it is like, you know, sorry, say.
I was saying, I could believe that because there are switching functions that are really bad for harvesting in terms of the noise they introduce.
Yeah. We had this very this back and forth with the referee regarding like what is actually pure harvesting and what is like, you know, you actually like the two detectors are not getting entangled through the field, but you know they are, because they are time like separated or space like separated, and therefore they're getting entangled because of that. And so there was all a discussion of, you know, the Feynman diagram of what's going on, and the fact that it's in many cases it's really hard to understand which contribution is which. Yeah, but definitely, yeah, you're right. If it's outside of the light cone, it's definitely
there's, I guess,
harvesting.
I'd like to get to the other questions if that's okay. So Gavin was next, and then we'll go with Magdalena and then Aki.
Thanks, Edu, for the question.
Oh, not a problem. Thank you.
Thanks, Valentina, for the great talk. Just a question, how does it affect the results on entanglement harvesting if you include particle statistics on the detectors, like say treat them as bosons or fermions?
Okay, my short answer is I don't know. So I guess, so you're saying like, how would you do that? So you're saying like treating the center of mass as like, I don't know, with a statistics like fermion statistics or boson statistics? Is that what you're asking me? Yeah. I don't know. Probably this is something that Hakim can answer.
Yeah, maybe. Yeah, I'd like to make a comment and then refer to Laura because she probably knows it better than I do. So the thing, I think as long as the two detectors' center of mass wave functions don't overlap, it probably shouldn't matter, right? But when they do overlap, then it will matter. Or when they want to overlap, then it will matter, right?
Right, yeah.
What are the circumstances? Did we consider, I mean, our wave functions always overlapped a little bit, right?
Yes, I think so, yeah.
Yeah, because
if you consider the separations, Right.
So then the question isn't the question, Gavin, is great. We just haven't considered it, but I think it would be naturally occurring as soon as they overlap significantly.
Yes. Okay.
Yeah, that's why I said I don't know yet, because we have at least I haven't thought about it. Maybe the others have.
So there's a question from Magdalena. The question is mass of an order of atomic mass enough to reach your high mass limit? So you want to address that, Valentina?
So you're saying mass in terms of an atomic mass big enough, small enough? Is that the
Yeah.
question? Let me see if I. Well, I think you have to compare it to. Gosh, I don't have the answer on top of my head, but I mean, it's a matter of comparing it with. I mean, it's more a matter like the I don't know. Maybe this is.
I think you're on the right track, Valentina. You have to compare with the free path length. You see the
Okay. Yes.
the
Yeah.
atom
Yeah.
will-
You also.
wave
Yeah.
function will decay. It will decay, right? It will spread the wave function, but then eventually it'll interact with something and it will collapse again. So I suppose as far as atoms can delocalize, it matters. And of course they can, right? It's just they don't have to. It depends on what their free mean path is.
Yep. Yeah.
Mm-hmm.
Yeah. So yeah, there's not like a threshold in terms of these things are mass, like these values of mass are, you know, classical. It's more like comparing it. Yes, as Akim said. Yeah.
Okay, so Akim, do you have another question?
Just a comment. As Valentina and Ed already pointed out, this is just the Klein-Gordon field, and in this sense, a toy model. And of course, it would need to be done with electromagnetism, and then extra features will occur, just as came up in Rich's work, and just generally because it's vector valued. But I would like to add that we didn't necessarily mean to just do just a toy model, right? For what really ought to be electromagnetism, because there are other examples where you would have detectors in fields. For example, you could have detector-like things in a Bose-Einstein condensate, and then the Bose-Einstein condensate has modes.
Right.
And then you could have, for example, ion traps, and then the ions themselves form a lattice, which is harmonically coupled, and you have modes in there, and you could couple to those and harvest entanglement from those. And so I just wanted to point out that this work can be generalized in multiple directions, and full electromagnetism is of course one way, but for example, for ion traps, I think there could be application.
Yep. Yeah. True. Yeah. I haven't. Yeah. When I wrote it that way, I haven't thought about the fact that light matter interaction in a certain way is one option, but one one can sort of create detectors in different ways. But actually, any other questions? Because I actually would like to ask Josh, like, what he thinks, because I don't remember exactly what he said about his excitation probabilities and so on. Like, if it's sort of, if what we have done rings the bell, like say, like, okay, if we take the specific limit, we can sort of connect the two approaches. Otherwise, we go on with questions.
No, I don't have any specific comments at the moment. I'll have to think about it a bit more.
Okay, yeah.
Maybe.
Yeah,
maybe
me too. When
can...
you said it, I was like, yeah.
Well, we're in the same time
as
zone,
Laura
so
said,
perhaps we can actually discuss it.
Yeah. As Laura said, it, she's interested too. I guess Akim and Nick too. Yeah. But yeah.
All right. Well, maybe we'll cut it there, so we have a 4-minute break, and people need to stretch or do whatever you need to do. And we'll be back in 4 minutes. Let's thank Valentina once again.
Thank you, everyone.
Okay, see you in a few minutes.
So, Nick, how does that work during the break? Is it possible to ask if the person is still here? Can I have, like, if it were a conversation with the speaker?
You can have it publicly.
I can. Yeah. That's what I mean. If that's okay.
Yeah, sure.
So that's for all of you, though, because Nick, Valentina, Laura, Achim, right, it says about this. So Valentina, you showed in one of the plots, right, how the probability, the excitation probability went down with mass when mass went to 0, and you were saying that that's likely because, right, the energy that you introduce with the time-dependent Hamiltonian, right, of varying the switching, goes into perhaps the center of mass, degrees of freedom, right? Is that something you suspect or something you've checked? It's like an intuition or more like something that you've computed? You're muted, by the way. Sorry, I can't hear you.
Have we checked it? We have the formula somewhere. Maybe Laura can say, because Laura, you go because you
I don't.
You guys have checked.
Interrupt. I
Go
don't.
on.
believe we explicitly checked this. However, we had good intuition for expecting that's the case. When we look at the full transition probability, there's expressions relating the recoil to the energy gap, and I'm trying to remember this, but relating the momentum of the, I guess in this case, the phonon and the energy gap of the detector, and I think the recoil, and those show up in multiple places. And so that's what led our intuition.
No, I believe the intuition has to be correct, but it comes to mind. One way to quickly check that comes to mind, right? You could imagine in the resulting state after evolution, you could for the partial state of the detector, including center of mass and internal, you can compute the expectation of the energy, the local terms, right? The term that is internal with the expectation of the energy of the center of mass one, which is a relatively easy calculation, right? And then you could compare and sure, you can check if what comes from the interaction term of if you do the expectation value of the interaction term, how that varies, the variation of that, how it distributes between all the terms after evolution, right? Because throughout evolution, energy is conserved. Well, no, because you have continuous dependence. It's not a sudden switching. So it's slightly more complicated. But at the very least, you could compare the internal expectation of energy, central mass expectation of energy, right? Because it's more where the energy goes, right, of the switching. I wonder.
Yeah, I was trying to see like if there is, because I didn't put the formula in because sometimes I think they're not that they're useful, but I was trying to understand, like in looking at the limits for those, one could understand. But yeah, as Laura mentioned, we probably said like, okay, that's what it's happening.
I would expect also that at some point, right, for small enough mass, the model is not going to be accurate anymore because the energy would make the detector relativistic, and then bye-bye. But at least
yeah, that's why we had to put this limits
right.
in here, like
right.
And yeah, and yeah, I think you sort of see the behavior here when the mass goes to zero, like
so one of the things we do in the paper, Richard and I, in the paper that you mentioned, at the end, we also look at what is the effect of relativistic corrections to this. And it's super interesting. I mean, obviously it's super complicated, but so it's not something that you can tell off the top of your head. But as you become more relativistic, there's a lot more mixing between internal and external degrees of freedom. So those non-trivialities may change that behavior, right, when you get to the relativistic limit there.
Okay, so we're gonna probably get started with the next session. That's all right.
So the name of Alex Pozas Kirchen, it was Alex.
Excellent. Okay.
I felt like Alex, I forgot. Sorry. Thank you.
All right.
Great talk.
So the next speaker is Sho. Is it Onoe? Sorry about the pronunciation. Is that correct?
Yeah, that's correct.
Okay, great. So Sho Onoe from the UQ, and he'll be talking about, oh, it's a different title. Realization of an under-DeWitt detector via electro-optic sampling. All right, take it away, Sho.
Okay, thank you for making time to watch this presentation. My name is Sho Onoe, a research fellow at University of Queensland, working under Professor Timothy Ralph. Today I'll be talking about my work on realization of an under-DeWitt detector via electro-optic sampling, which was a work done in collaboration with experimentalists as well as theoreticians in Korean Advanced Institute of Science and Technology, as well as University of Constance. First, I'd like to talk about electro-optic sampling, which is a detection scheme that allows one to probe the terahertz signal in the time domain. This technique was developed from the 1990s through to the 2000s, and some of the notable development of this technique can be found in these papers presented here, of which some were written by my collaborators. I've shown the rough schematic setup of electro-optic sampling in this figure here. And basically how it works is you utilize a near-infrared signal with a femtosecond probe pulse, represented by this red line here. And then you interact this probe pulse with a terahertz signal represented by this navy line. We interact it through a nonlinear crystal, and this setup allows one to basically compute the intensity that overlaps between the electric field of the probe pulse and the terahertz signal, allowing one to measure the terahertz field with a femtosecond resolution. We then change the delay time as such, and if we conduct enough measurements, we can effectively reconstruct the terahertz signal in the time domain as so. The advantage of utilizing this technique over, for example, homodyne detection scheme is that we have this few femtosecond resolution. This resolution is actually less than one period of the terahertz signal, meaning that you can probe the terahertz signal at a subcycle regime. However, if you utilize homodyne detection, for example, you can at most measure the terahertz signal with an accuracy of a few cycles, and you cannot have this time resolution I have shown here. And therefore, this technique remained an important tool in quantum optics. And in 2015, they were able to push the limits of electro-optic sampling to the quantum regime. In this paper, they probed the quantum vacuum fluctuation. So in this figure here, I have shown the vacuum fluctuation in the red line. Now, if you probe the vacuum fluctuation over a long period of time, say 100 femtoseconds, then you average over all these fluctuations and it average out to be 0. And this can be compared to, for example, homodyne detection, where if you average over a few cycles, you only see shot noise variance. And we observe an analogous result for the 100 femtosecond result represented by this black line here. Now, since we're using electro-optic sampling, we can probe the vacuum fluctuation at an accuracy of the subcycle regime. And when we do this, we find that there is extra noise. In this paper, they looked into the property of this noise, and they found that it is consistent with the Heisenberg uncertainty principle. And from this, they concluded that they were actually probing the quantum vacuum fluctuations. However, this result was met with suspicion. There are no analogous technique that is well established in the field of quantum optics, and people started to wonder, are we actually detecting the quantum vacuum fluctuation, or are we just seeing extra noise that is inherent to the detection scheme? And so we looked into this problem deeper, and then we asked ourselves, can we understand electro-optic sampling, quantum electro-optic sampling through an analogy to its classical counterpart? And this is basically where our work comes in. And we answered the question, does electro-optic sampling actually probe the vacuum fluctuation through its analogy to an Unruh-DeWitt detector? And we showed that in certain operational regime, this is indeed the case. Electro-optic sampling is also a little vague in its interpretation and is referred to as an ultra-broadband detector that can probe at an accuracy of few femtosecond. We plan to understand this at a deeper level by utilizing a modal decomposition and identifying the exact modal shape of the mode you are probing, the terahertz mode you are probing. And lastly, since we make an analogy between Unruh-DeWitt detector and electro-optic sampling, we ask ourselves, can we actually realize an Unruh-DeWitt detector in the lab through electro-optic sampling? And we finished this presentation with a proposal for an experimental demonstration of an Unruh-DeWitt detector. Before going into the details of electro-optic sampling and Unruh-DeWitt detectors, I'd like to talk about the virtual particles and antiparticles that exist in the quantum vacuum. So I have plotted the vacuum fluctuation in the figure on the left, normalized by some constant factor E0. And then from this result, we can square the electric field and compute its effective variance. So the variance E squared on I01 is analogous to short noise variance. And let's look at this a little deeper. So we see that it oscillates around 1, but is not actually constant at 1. And this means that if you look at a localized time, you can have on average variance that is larger than 1 and variance which is lower than 1. So for example, we can associate the average variance above 1 with virtual particles and average variance below 1 with virtual antiparticles. Now, since virtual particles and antiparticles annihilate each other, if let's consider a case where T is equal, 100 T0 is equal to 1 period, then if you utilize, for example, standard homodyne detection scheme, you would detect all of these particles and virtual particles, and they would annihilate each other, and you're left with just short noise variance. However, if we utilize a detection scheme which allows probing the vacuum at the subcycle regime, for example, let's say we probe the vacuum fluctuation between 20 to 60, then we would only see these particles, and the virtual particle will annihilate the antiparticle, and you will see an extra virtual particle. And this will contribute to a variance that is above 1. Now, if we compare to this to the result where we probe from 10 to 50, for example, you see one virtual particle and 2 virtual antiparticles. The virtual particle will annihilate the virtual antiparticle, and your detector will overlap with 1 virtual antiparticle. However, your detector cannot see -1 amount of particle, and therefore this virtual antiparticles remain unobserved by your detector. So if you average over variances that is above 1 and variance that is just equal to 1 because the virtual particle is not detected, you get an average that is above 1. And another feature I'd like to talk about is the entanglement that exists between virtual particles and virtual antiparticles. So the virtual antiparticle is generally entangled to the virtual particle in such a way that if you observe 3 virtual particles, you are more likely to only observe an even amount. You will more likely observe another virtual antiparticle, and you will more likely observe an even amount of particles. When this entanglement is perfect, you will only see an even amount of particles, virtual particles, and that corresponds to the subcycle mode having squeeze statistics. So I'd like to put this notion in more rigorous terms by looking into subcycle Gaussian profile mode. So a Gaussian profile mode has frequency omega g with a period that's related to pi on omega g, and its temporal width is related to sigma g, and we can change the sigma g arbitrarily. If we make sigma g small enough that there's only roughly 1 cycle within the Gaussian profile mode, then you enter the subcycle regime, and we predict that you can see virtual particles and antiparticles for this subcycle Gaussian mode. We computed the statistic of this and found the following. So if the Gaussian profile is much larger than the wavelength, then you are in the standard regime where there are no virtual particles in the subcycle regime. So if you conduct standard homodyne detection, you'll be around here, and you will just see short noise variance. However, if you go into the subcycle regime, we find that the subcycle mode is populated with virtual particles. For a Gaussian profile mode, you are able to couple with the virtual antiparticle, and you see an indirect evidence of its existence as you see squeezing. However, this coupling is not perfect, and therefore this blue line does not completely align with the VMUS, which is the minimum variance for a minimum uncertainty state, which corresponds to a single mode squeeze state. But nevertheless, the important feature is that the variance goes below, you are able to observe variance below 1. Now that we've talked about virtual particles, I'd like to talk about how we actually detect these virtual particles. And this virtual particle can be detected through an Unruh DeWitt detector of the following form. We consider an Unruh DeWitt detector with a harmonic oscillator degree of freedom, not a two-level system, with energy h bar omega u. So this annihilation operator satisfies the bosonic commutation relation. And we consider an Unruh DeWitt detector which is stationary and interacts with the conjugate field with a switching function lambda. And when we tailor the switching function to match this profile of the subcycle mode and the energy of the Unruh DeWitt detector to equal the frequency of the subcycle Gaussian mode, we find that the Unruh DeWitt detector is able to couple with this subcycle Gaussian mode in an action that is similar to a beam splitter one. And what this means is, for example, let's say consider a case where the subcycle Gaussian profile mode is populated with one virtual particle. And this coupling allows one to promote this one virtual particle to real excitations of the Unruh DeWitt detector. And so after this interaction, if you see one excitation in the Unruh DeWitt detector, this means that there must have been one virtual particle in the subcycle mode. And this beam splitter model allows us to model the evolution of the detector as follows. And if we measure the quadrature moments, we find that the first moment is cos theta of what was already in the detector plus sine theta of what was in the subcycle mode. And the second order moment, so the variance, will equal cos squared of what was in the Unruh DeWitt detector plus sine squared of what was in the subcycle mode. And for example, if there was no virtual particle in the subcycle mode, then you would just have cos squared plus sine squared, which is equal to 1, and you would just see short noise variance. So this is consistent with the properties of the subcycle mode. So now I'd like to take this point to conduct an intermediate summary. So a subcycle Gaussian, the subcycle Gaussian statistic in the vacuum is that it is populated with virtual particles, and they is strong coupling with virtual antiparticles, so that you see you are more likely to see an even amount of virtual particles in the subcycle mode. We're able to show a well-defined waveform with which the Unruh DeWitt detector couples to. So for example, if you tailor the Unruh DeWitt detector's switching function to that of a Gaussian profile and energy sufficiently small, you can you couple with a Gaussian profile mode of that exact switching function and frequency. We're able to show the interaction between the Unruh DeWitt detector and the subcycle mode is that of a beam splitter, which means that the excitation observed in the Unruh DeWitt detector corresponds directly to the existence of virtual particles. Now we'd like to utilize this Unruh DeWitt detector model to explain electro-optic sampling. So in an electro-optic sampling, you interact the electric fields through the nonlinear crystal, and the interaction Hamiltonian inside the crystal is represented by this Hamiltonian here. EZ is in the electric field in the Z polarization, ES is the electric field in the S polarization. The rectangular function is associated with the finite length of the electro-optic crystal. And since we couple the Z polarization with a strong coherent signal, so you can approximate EZ with that of a classical probe strength. And we simplify the electric field in the S polarization to the low frequency regime and the high frequency regime, where the high frequency regime is the near infrared regime. So if we split it up in the frequency basis, it looks like this. So you utilize a strong coherent signal in the Z polarization and couple it to the field. And then this stronger coherent signal allows one to couple the high frequency electric field with the low frequency electric field in the terahertz regime. And we'd like to conduct a Unruh DeWitt detector model to this. And we do this by comparing the Hamiltonian. So if we look at the Hamiltonian, if we compare the Hamiltonian of the nonlinear crystal and the Unruh DeWitt detector, we can associate the classical probe pulse with the switching function, the high frequency mode with the harmonic oscillator of your Unruh DeWitt detector, and the low frequency mode to the conjugate field. And by doing so, we replace this with the switching function, the high frequency mode with your Unruh DeWitt detector, and the low frequency mode with your conjugate field. However, one issue with this analogy is that the harmonic oscillator in the high frequency regime has a continuous amount of harmonic oscillators, as opposed to compared to, for example, the Unruh DeWitt detector, where there is only one harmonic oscillator. And we go about this problem by introducing a narrow band localized mode of the following form. And delta omega can be as small as you can achieve in an experiment. And for example, let's say you can achieve delta omega that is of 1 terahertz, then you can fit effectively 100 Unruh DeWitt detectors in this regime. Yep, and then we'd like to see the interaction that occurs between the harmonic oscillator you assign the role of Unruh DeWitt detector and the subcycle mode. And what we find is if we compute the integral that if we utilize the Unruh DeWitt approach, we can, at certain regimes, you can model the interaction through a beam splitter interaction between the subcycle mode and your effective Unruh DeWitt detector, and a squeezing interaction between the subcycle mode and the Unruh DeWitt detector. So this interaction is good because it, it's similar to the Unruh DeWitt detector. However, this interaction is not so good because this interaction basically creates 2 photons both in the subcycle regime and in the effective Unruh DeWitt detector. And this creation of particle is not related to the existence of virtual particles in the subcycle mode. And so the question we asked is there a way to get rid of each other and, ideally just have the beam splitter type interaction between the Unruh DeWitt detector and the subcycle mode? And to answer this question, we utilize a technique we refer to as first order unitary evolution. Basically, what this technique states is that when computing the evolution of just one of these Unruh DeWitt detectors, you can kind of forget about the interaction associated with all the other Unruh DeWitt detectors. So for example, you can approximate the whole Hamiltonian with just the part that interacts with your Unruh DeWitt detector. This is actually different to, for example, first order perturbation theory, which conducts an approximation to the evolution. In this case, we conduct an approximation to the action itself. and therefore we can create analogies between the action. In the beam splitter regime, we can conduct the first order unitary approximation and model the interaction through a beam splitter, and we get a result that is analogous to the one we observed for the unary DeWitt detector. The main feature being if the subcycle mode is in the vacuum state, cos squared plus sine squared is also 0, and you do not see any virtual particles that weren't there. On the contrary, if you utilize the squeezing regime, the quadrature moment evolves as follows. You have the cosh instead of cos and shine instead of the shine. This is an issue because if, for example, the subcycle mode was actually in a vacuum state and does not have virtual particles, you would see cosh squared plus shine squared, and this is above 1, and you cannot associate the extra noise you observe in your unary DeWitt detector with the existence of the virtual particle in the subcycle mode. And we plot the result in the regime where we put this harmonic oscillator as small as possible and obtain this result. So to the left of this line, it is associated with the squeezing interaction, while to the right of this line, the interaction can be associated with the unary DeWitt detector model. Now, the frequency of the unary DeWitt detector is effectively associated between the difference between this frequency and the frequency you actually probe. So, for example, if you probe 300 terahertz, that corresponds to an unary DeWitt detector that is roughly 45 terahertz in its frequency. In this case, we have considered a probe pulse that is constant, so sigma g is constant, and we vary the associated frequency. So if we go near this line, we enter a more subcycle regime. Now, if we recall an earlier plot, we showed how if you become more subcycle, you have more squeezing and more particles. However, in this plot, you see that around here, you have less squeezing, even though you enter a more subcycle regime. And this is associated with the fact that the interaction strength between your unary DeWitt detector and your subcycle mode decreases at a rate faster than faster than the rate at which the population of the unary virtual particles increases in the subcycle mode. However, if you just look at this plot here, and if you just mirror the result, it is quite analogous to the prediction we made for the subcycle Gaussian mode, which is good. And now I'd like to show the exact waveform that you probe through electro-optic sampling. So if you utilize an unary DeWitt detector, we showed that you probe a subcycle mode which has the exact waveform of the Gaussian profile multiplied by the frequency you probe. However, for the electro-optic sampling, this is not the case. So if you interact, if you utilize a probe pulse of a Gaussian waveform and interact it with the subcycle mode, the subcycle mode you interact with is of this form, represented by the light blue line. And we find that this is slightly larger than the Gaussian profile which you drive the interaction. And this is actually associated with the peculiar property of the nonlinear crystal due to phase matching. And if we were able to utilize a nonlinear crystal with perfect phase matching, this blue line will coincide with the navy line. But nevertheless, roughly speaking, if you utilize electro-optic sampling, we find that the you probe a Gaussian profile mode of frequency omega minus omega p, which is the dashed line we saw in the earlier plot, with, roughly speaking, a Gaussian profile that is slightly larger than the one you drove the interaction with. And now I'd like to talk about the experimental feasibility. So this setup basically shows how you would conduct the experiment I have talked about with the Unruh DeWitt detector model. Basically, it is identical to electro-optic sampling. However, you utilize a detector which filters out everything apart from the frequency of interest. And this is done through utilizing low pass filter and high pass filter. And ideally, we want to make this as narrow as possible so that it mimics the Unruh DeWitt detector as closely as possible. And in an experiment, they have already reached 10 terahertz, and they have already obtained some experimental result. And if we just push this a little further, we will be able to reproduce the results of an Unruh DeWitt detector in the lab. So in summary, we answered the question, does one actually probe the vacuum fluctuation in electro-optic sampling? And we said that yes, it does, as long as you put this filtering after your standard electro-optic sampling technique. We were able to answer the question, which mode does electro-optic sampling actually probe, by identifying the wave packet mode that the electro-optic sampling interacts with through a modal decomposition. We have also shown that this can be reproduced in the lab just through introducing high pass and low pass band filters after the standard electro-optic sampling technique. Now I'd like to talk about the future work. We'd like to propose this electro-optic sampling as a new kind of Unruh DeWitt detector and push this research direction. And the first step in doing this is to experimentally verify the result I have shown you in a few slides earlier, where I plotted the X and P variance. Next, I'd ideally want to consider the case where you can have effectively two Unruh DeWitt detectors that are delocalized in space. And it would be nice if we can show that we can get the two effective Unruh DeWitt detectors to be entangled, showing the existence of vacuum entanglement and showing entanglement harvesting. And lastly, it would be nice to apply this detection scheme to scenarios beyond the vacuum state, and specifically utilize a specially designed quantum system that possesses tailored effective metric through which the particles propagate. So by doing so, we can effectively utilize the Unruh DeWitt detector in curved space-time. Thank you for listening. That will conclude my talk.
All right. Do a bit of clapping. Excellent. So do we have any questions for show? So you can put questions in the chat, or you can just raise your hand. Give people a minute. Oh, Rob's got a question. Rob, go for it.
Yeah, hi, Shel, thanks. I think that's quite interesting work. I just wondered, can you say a bit more about noise sources for all of this? I mean, it sounds a bit too good to be true.
What do you mean by the noise source?
Well, I mean, there's going to be, where's the biggest source of experimental error in all of this?
Right, so that's what they've been basically working on from the 2000 through to 2015. There's, you need to be able to, let me just go back. So this electric optic field that you create has to be super stable so that, you're interacting with exactly the same, exactly the same mode. And there's some minor technical difficulties with the optical setup and how, like, for example, there's change of refractive index in these optical elements, and you need to be sure that the noise you're measuring is not associated with those factors, but exactly that. But those are the problems they basically worked on for 15 years, and they were finally able to push it to the quantum regime. So I guess my answer is, that is the first question they looked at when they wanted to push electro-optic sampling to the quantum regime.
Well, okay, I guess I'm just thinking that you're trying to actually see if you can identify entanglement with virtual particles and so on. I mean, does that not, I mean, do you think all the errors are under control in doing that?
Right. Well, for one, duality detectors, I think they've got it all sorted out. But if you want two duality detectors at two locally spaced intervals, there's a long way to that. And you're exactly right. There's a lot of issues with that. Firstly, you need to be able to make two signals coherently at a fixed distance apart from them, or fixed time interval. And you would need to be able to utilize two detectors. So you would have one detector measuring the first, pulse, and then you need to be able to change, switch something so that the second pulse enters a different detector. And I think we're very far from utilizing two detectors, where if you use two detectors, you can do entanglement harvesting. But I think we're close enough to look at correlations, and we're looking into showing correlations, but not into harvesting vacuum entanglement yet.
Okay, thanks. Oh, and one other, did you, can you go to the first slide? Is there an archive number for this thing?
So I'm writing this paper with lots of professors, and they're all busy. It's at the final draft stage, but we're still waiting for all the professors to read it before we can put it on archive, and hopefully we can put it on archive within 2 months. But yeah, it's still not on archive yet.
Okay, I tried to find it and I couldn't, so all right, that's why. Okay, thanks.
Yes.
Okay, do we have any other questions? Gonna lower Rob's hand here. There we go. Unless you had another question, Rob, but otherwise I'm assuming that
No,
was a
sorry
legacy
about
hand.
that. I missed that.
All good. All good. Yeah, so we've got a couple minutes. If there are other questions. Well, if there's a thumbs up, is that a raised hand?
Sorry, I didn't know how to raise hand, so yeah, sorry.
Yeah, under reactions, it's the very bottom. It says raise hand, but that's okay. Go for it.
Okay, yeah, I'm just a newbie in this field, so the question is just a simple the vacuum, does it really fluctuate, or because the figure that you showed is that it feels like it has, the electric field has definite value at all times, but which may not be may not be true. So can you be more clear on this point?
So the figure I showed here is a very classical representation of the vacuum fluctuation. It's not like this. Like this would be a one-shot measurement of the electric field fluctuation, fluctuating around some some E naught. I mean, no, the electric field strength. And like, for example, if you were to associate this with particle numbers, for example, you would see electric field with Personnian statistic, and that Personnian statistic is associated with vacuum, well, the shock noise variance. But if you look at Personnian statistic for a short time, you would inherently, observe some feature which is has more noise than Personnian statistics and less noise than Personnian statistics. So that's related to the vacuum fluctuation. And if you look for a long enough time, it's a well-defined Personnian statistic. And so you kind of expect there should be vacuum fluctuation from that point. You don't expect perfect Personnian statistics for all time. And you can associate that with vacuum fluctuations.
Okay, so your figure is just classical picture.
Yes.
Okay, then okay, thank you for this. And also, can I have one more question?
Yeah, go for
would
it.
you just would you elaborate the relation between the virtual particles and these fluctuation? Because I don't know what do you mean by virtual particles exactly? Is it like
virtual particles are, for example, if you have an accelerated observer, or like Hawking radiation is, or like the analogous of Hawking radiation is the Unruh radiation, and basically an accelerated observer sees particles in the quantum vacuum. And the fact that you see, particles in the vacuum is why we call it virtual particles. If in a certain frame they're actually particles, but in the rest frame they're not meant to be then. That's why we just call it virtual particles.
so it's virtual because it is only seen by the accelerating observers?
Yeah. One example where you can see virtual particles is accelerated observers.
Okay. Then you mean the particles by like any particles, like with any spin or any like masses, or is there any?
So there's been research into like particles with spin and stuff, and if you accelerate fast enough, then you can. There's been research onto Unruh detectors with spin degree of freedom and seeing how the orbital momentum is affected by these virtual particles, and I forgot the details, but I think these virtual particles can have spin. I read this paper a long time ago, but yeah.
All right, I think we may have to move on.
Thank you very much.
By the way, those questions are very good questions, and they are very fundamental questions. And it's where are you at? Who's the person that asked Seongjin? I don't know if I'm saying it right. Where are you?
Yeah, I'm at Korean Advanced Institute of Science and Technology, KAIST, at Korea.
Okay.
And
so
I'm under. Yep.
I'm sorry, you cut out when you said who you're working with. Who are you working with?
Sorry. So I'm working in KAIST in Korea.
Okay.
I'm working with Andre Moscato.
Okay, so it would be good to talk to someone locally about these questions, because they're good questions and they're hard questions. But we're going to move on. Sure, we're going to move on. So the next presenter is Gavin Brennan. Hey, Gavin, you want to share your screen?
Yeah.
All right. Okay, so our final presenter today is Gavin Brennan from Macquarie. He's going to talk about quantum simulations of holographic duality. Take it away, Gavin.
Thanks, Nick, and thanks for the invite.
Oh yeah, so just so it's a 30-minute talk, 10-minute questions.
Okay, just can you see my slides advancing?
Not yet.
No? Oh, great. Still not?
Well, I can see the first slide now. I'm seeing the presentation.
All right, I'll just have to do it this way, I guess. For some reason it's not working. Okay, yeah, so this is work done with Suki Singh, who is at Freie Universität Berlin, and also Max Planck Institute for Gravitational Physics, and my former student, Nathan McMahon, who's at FAU Erlangen. So what we were aiming to do in this project that has been going on for actually a few years now is to understand if there's a kind of microscopic understanding we can have at the level of quantum information theory, and particularly quantum simulation, to capture some of the ideas behind the holographic principle. And what I mean by that is, the general idea that there could be a volume of space that could be encoded on the boundary of a space. And if you look up holographic principle in say Wikipedia, you might see a figure like this with lots of strings around there, and they'll talk about 5-dimensional anti-de Sitter space-time and black holes and so forth. And we just want to understand some of the basic features of this without going to string theory. This holographic principle has been quite useful for studying black hole thermodynamics and the anti-de Sitter conformal field theory conjecture, or ADS-CFT. And so after some back and forth and misstarts, I think we've arrived at a construction which does indeed capture a lot of these features. And it actually has a relatively straightforward picture. So you can find the details in this paper from last year. Okay, so what do we mean by holographic correspondence? Well, we mean that there's an equivalence between a theory of gravity in d-dimensional spacetime and a quantum field theory without gravity in one lesser dimension. So we can see it as something of a quantum field theory living on the boundary of a d-dimensional spacetime, and the extra dimension carries the information about the renormalization group flow of the boundary theory. And if you don't know what I mean by that, I'll get a little bit concrete in a few slides coming up. But one of the concrete realizations of this idea, which actually goes back several decades, was the ADS-CFT correspondence proposed by Juan Matachena and also Edward Witten. And it's just visualized here, where you can think of a cylinder where a one spatial plus one time dimensional conformal field theory lives, say, on the perimeter with time going up, and on the bulk side, you would think of it as kind of a disk, but with hyperbolic geometry moving forward in time. Okay, so often this is studied in what's called the semi-classical regime, where we mean that the radius of curvature of the gravity side is large. A picture here is that you might have a description of a conformal field theory on the boundary of a system. Here it's just this ring, and we have some spatial coordinate x along the ring. And then there's another dimension z, which goes into the bulk. And this bulk has anti-de Sitter geometry. And so straight lines, the geodesics, look curved if you project them onto Euclidean geometry. And it was calculated in a famous paper in 2006 by Ryu and Tagenaki that the entanglement entropy of a region of the boundary conformal field theory, where the length of the conformal field theory, which is in a flat space, would have, say, length script L, would have an entanglement entropy that scales like central charge times logarithm of L. And the central charge is a physical property of the conformal field theory that is actually proportional to the radius of curvature of the bulk dual in the curve space. And what Rio and Takenaki showed is that this entanglement entropy can actually be understood as the length of a geodesic computed in a bulk space where the radius of curvature is given by capital R. So now usually those theories are studied when the central charge is large, so the radius of curvature is very large. You don't have a lot of curvature in your bulk. But actually, there are some studies of conformal field theories with small central charge being dual to quantum gravity in a bulk. And a notable example is this paper that describes the gravity dual of the Ising model. The Ising model is a conformal field theory of, you can just describe it as a bunch of quantum mechanical spins in a 1D geometry with some nearest neighbor Ising coupling and a local magnetic field in a perpendicular direction. And these authors show that there is actually a well-defined partition function description of the bulk dual for that Ising model. We're going to use the formalism of tensor networks to further probe this and see if we can get a really good understanding of the quantum mechanical features of the bulk. So one other feature that shows up in the ADS-CFT correspondence is what's known as a gauging of boundary symmetries. So if you have a boundary state, so let's say you have a conformal field theory on a ring, and it has a global symmetry, meaning if you apply the same group element to every point in space, or here I've described it as a lattice, then the state looks the same. That just means it has a boundary global symmetry. And one of the predictions of ADS-CFT is that the corresponding bulk state to this boundary state should have a local symmetry. That is, if you go into the bulk and you apply a local symmetry, which could differ at different points in space, you get the same bulk state back. So if we want to have any kind of construction of a quantum state that reveals some of these features, we should be able to see this physics arising out of that. All right, so in particular, these symmetries are describing gauge fields where a gauge field is valued in the algebra of the boundary symmetry group. So for example, if the boundary symmetry group was Z2 symmetry, like a spin flip symmetry, then you would say that the gauge field is a Z2 field. And in the quantum gravity regime, the bulk vacuum is entangled between the gauge and the remaining bulk degrees of freedom. So we're going to see how that arises. So let me talk about how one could actually build a conformal field theory on a lattice of quantum spins. So just for simplicity, let's describe an infinite one-dimensional quantum lattice where each site carries a spin, a qubit, an atom, etc. And we'll consider a Hamiltonian acting on these spins, which is local, meaning it only involves coupling between a few nearest neighbors, translational invariant, and it's critical. That is, that in the continuum, it would be described by conformal field theory. And we want to have a way to describe the ground states of this Hamiltonian, which is conformal field theory. Well, a very convenient technique to do this is using a tensor network, which is just an assemblage of matrices that are combined together on, say, your classical laptop that give a description of this ground state. So we could write the state here as, a sum over all possible spin states on the boundary with some coefficients. And this state will generally have d to the n coefficients if the local Hilbert space dimension is d. But you can represent it using this thing called a Mera network. a multi-scale entanglement renormalization ansatz invented by Guy Vidal back in 2007. And it's just another way to write down this state where you're representing it in terms, you're representing each one of the coefficients of the expansion of the state in terms of the contraction of this, this network on the right-hand side. So each one of those boxes and triangles contains numbers. The boxes are unitaries. So if you apply U and U dagger, you get the identity. And the triangles are what are known as isometries. They change the number of degrees of freedom from the input to the output, but they satisfy the condition that if you apply W dagger followed by W, you get the identity operator. And in the tensor network, we have this bond index, which tells you how you multiply these matrices together. And at the bottom, you have these open indices, and those correspond to physical degrees of freedom. So actually, there's a very nice way to see how one would build such a conformal field theory using the information about your Mera tensor network. So you can actually think about this picture as describing the flow of a quantum circuit where you start off at the top, and at each point you see a zero. There's an initialized zero state of, say, your qubit, and you apply a unitary gate. Where you see an isometry, you can extend that to being a unitary when you attach these degrees of freedom prepared in a zero state. So then actually this whole circuit with the boxes and the triangles describes a circuit with unitary gates everywhere. And at the end, you will have a big entangled state of all these degrees of freedom, which is going to approximate a conformal field theory when you choose your unitaries and these little gates to have the numbers that you obtained from your description of the tensor network. And it's notable that this circuit is a log depth circuit in the size of the boundary. So it's an efficient thing to produce. You could imagine it being done in nearish term quantum devices. The Mera encodes the renormalization group flow of the ground state in the sense that each layer of tensors implements a coarse graining transformation. So you can think of the physical degrees of freedom at the bottom as sort of the ultraviolet limit up to your lattice spacing. And then if you discard the bottom layers, then you get new degrees of freedom, which are like coarse graining degrees of freedom. And going further up, you get eventually a coarsest scale description of your system, which for conformal field theories actually captures all the physics. And some notable features about the Mera is that it has kind of built in a hyperbolic geometry. So we should view each one of these polygons as having the same area. And notably, you can think about a causal cone that relates to boundary sites that are separated by distance L on the boundary as having a number of bonds in the net tensor network that scales like the logarithm of the L. So in fact, there's a sort of built-in entanglement structure which you expect from a conformal field theory, namely that the entanglement of a sequence of L sites should scale like the log of L. Okay, so what we did is we wanted to have a quantum mechanical description of a bulk state that would be dual to a boundary CFT. So we take a Mera. So you've worked out what the numbers in these boxes should be to give a good approximation of a CFT. And we introduce some physical degrees of freedom on the bonds of the Mera. And we call these things bulk sites. So in fact, we're going to have 2 bulk sites per bond degree of freedom. And how do you do this? Well, you describe this in terms of some new tensors you put on those bonds. And it's actually highly constrained the type of tensors you can put on there. So we describe that the set of tensors you can apply there in terms of what we call 3 lifting axioms. And these are axioms that guide the description so that it satisfies features that you want to have. So one is that we would like our lifting tensors to be able to recover just the boundary state under local projections of each pair with a Bell state. So that means we have a way to locally project back down to the boundary state, acting on these bulk states. The second is that we would like this lifting tensor to be an isometry, which is important for satisfying some entanglement structures I'll describe in a few minutes. And also it turns out that this allows you to guarantee that the lifted Mera state is also efficiently constructible as a quantum circuit. So it's still a log depth quantum circuit, something that could be done in the laboratory in principle. And finally, we want the lifting tensor to be covariant under a change of bases along the bonds of the network. And this guarantees that any entanglement within the bulk doesn't depend upon the basis that you choose to represent your tensors there in the bulk. So it's naturally basis independent. And when you enforce all those axioms, it turns out that you get a reduced form of this lifting tensor, which is a sum of 2 diagrams with some adjustable weights that are actually free to adjust. And it's described by these coefficients alpha, beta, and chi. And actually, it can all be reduced to really just one parameter, which we call eta. And eta takes 2 limits, either 1 or chi, where chi is the so-called bond dimension of the network. It tells you how many different values those bonds of your Mera network can take. The case of eta equals 1 is just having an unlifted Mera. It would just be like a normal Mera with all the bulk degrees of freedom decoupled. And the case eta equals chi gives you a bunch of decoupled network sites inside the bulk. But in between, you get some correlations between them. And in fact, you can prove that the bulk is short-range correlated. So if you consider 2 bulk operators of the same height in this lifted Mera, then you can compute the correlations between them. And this is done by taking a contraction of these site operators along what are called spines of the network. So it's sort of this funny looking diagram with these spines that just represent the arrangements of tensors when you compute these correlations. And you find that indeed 2 bulk operators have exponentially decaying correlations with a correlation length that can be computed from this transfer matrix of the network. And also we get a feature which is the renormalization of boundary operators, which is a key feature that arises in conformal field theories, also is captured by our lifted Mera state. So a prominent feature of conformal field theories is that there exists scale invariant operators. And these give you access to the primary physical data of the theory, like primary and secondary fields. And a key feature of them is that they satisfy a scaling dimension, so that if you renormalize one of these boundaries scale invariant operators, you get the same operator up to some factor, which depends on what's called the scaling dimension. And this is also captured in our construction, when you can obtain a kind of a bulk correspondence to a renormalized boundary operator, but it ends up having a modified scaling dimension, which depends upon the bond dimension of your network. But that's something you can control in your description. And it turns out that this construction of ours has this feature of being what's called a strange correlator. And this is not a name I made up. It's kind of funny, there actually is a paper published in 2013, which just invents this name strange correlator, for lack of a better name, I guess. And what it means is that you can describe the overlap of a short-range correlated state with a product state as being the partition function of a critical model. So it's kind of a funny notion that you take a short range correlated state and you just contract it with a product state, and you get a number out which is associated to a critical state, which seems very odd because a critical state is involving long range correlations. But in fact, it does exist, and our construction is an explicit example of that. If you view our lifted Mera network as something which is short range correlated, which it is, because I just described that a couple of slides ago, and you contract it with bell pairs at every bulk site, then you get back to the boundary Mera, which is a critical state. And then if you contract that critical state with a product state of pluses on all the boundary sites, that corresponds to the partition function of a critical model at some temperature. So in fact, our construction is an explicit realization of a strange correlator for this model. So a feature that we find reminiscent of holographic duality is the existence of what's called a screen, holographic screen. And that is a codimension 1 surface which carries all the information about degrees of freedom inside that surface. So I've illustrated here a kind of pink screen called gamma A, and that's a geodesic connecting the two boundary points of this region A on the boundary. And it turns out that by construction using our tensor network, that all the information on this holographic screen, gamma A, is contained inside the wedge here, this yellow region, and vice versa. So it's a real explicit demonstration of holography. And it arises because the two reduced density matrices are related to each other by an isometry. And so all the spectral information and the eigenstates are contained therein. And a feature of this is that it allows us to actually calculate the bulk entropy, that is the entropy along a geodesic in our lifted bulk state. And what we do is we propose an entropy on the dual geodesic as a measure of length inside this bulk geometry. It turns out you can show that by the subadditivity of entropy that this definition satisfies a triangle inequality, which any measure of length should. And it makes the connection explicit between the Ryo-Tagenaki formula, which I described earlier, which related the entropy of a region of a CFT to a bulk length. But now where the bulk is not just some classical geometry where you can go in and easily measure length, but something where it's really a quantum mechanical state. And so we've chosen a way to measure length in this quantum bulk via entropy along this path, this dual geodesic path. So it's really a graph path. There's no intrinsic length associated with the lines on that geodesic. We're treating the entropy along that path as a measure of the length. But what we find is that because this is a quantum mechanical bulk, there is a correction to the Ryo-Tagenaki formula, which is related to the entanglement of the purely bulk degrees of freedom in this wedge with the rest of the network. So that's because we have an intrinsically quantum mechanical bulk. Okay, so one final feature we want to capture is this symmetry property I introduced earlier. So it's well known that a global on-site symmetry of a boundary conformal field theory can be forced exactly using local symmetric tensors in a Mera network. So what we mean by locally symmetric is every time you see one of these unitary boxes, you would demand that if you were to conjugate this by some elements of a symmetry group, you get the same unitary back. And similarly for the isometries, these triangles that show up in the network. So that's known, and it's just, you can show it by construction that you will have the boundary global symmetry preserved if you use locally symmetric tensors. What's not so obvious, but nonetheless true, is that in fact, if you want to preserve the global symmetry at all length scales, then the tensors must be locally symmetric. And I won't go through the proof, but it's described in this paper here. And basically, it arises because you have to have the symmetry preserved at all length scales. Another way to state that is that the anomalies are conserved at different length scales. So that's very interesting that actually you get an if and only if the mirrors are involving tensors that are symmetric, then you have a symmetry preserved at all length scales. So I'm getting near the end here, but you can, in your tensor network, in this lifted Mera tensor network, you can enforce symmetries of all the tensors, including the lifting tensors. And also this will guarantee it's an efficient construction of the quantum circuit. And then you get this gauging property here. So here's a piece of this bulk dual, where this lifted Mera, where I've applied some gauge symmetry on some physical degrees of freedom in this green area and the orange area. And because of the symmetry of the lifting tensors, this gets contracted down to a symmetry that acts on the tensors of the Mera itself. But because those are symmetric, they just disappear and you get the same state back. So that's the local gauge invariance. Well, I'll just skip this. This is just another restatement about the holographic screen allowing you a way to connect bulk entropies and boundary entropies. And to test our construction, we did some numerics for a family of unitary minimal model conformal field theories, which are a set of conformal field theories with a central charge that is small in the sense that it's less than 1, and it's given by this equation down at the bottom there. K is an integer here, which labels the type of theory. And there's a way to construct this using a chain of antiferromagnetically coupled anyons described by quantum group SU2 level K, where you have a pair of anyons that are spin half irreps that fuse into the trivial irrep. And what we did is we measured the entropy density of the phenomenon, or sorry, the Renyi-2 entropy along the bulk, and wanted to compare it with the Ryō-Tagenaki formula, namely to show that there is an increase in this entropy density that scales linearly with the central charge of the theory. So we did this for 7 different conformal field theories with different values K. And indeed, we do find that it's growing, well, certainly monotonically with these red circles, but it is growing with the central charge. And the way you calculate these things is with this contraction network on the right-hand side here. So this was an enormously difficult and long computation, which Nathan succeeded in doing. So let me just conclude here with some observations. The lifted Mera state captures both bulk and boundary degrees of freedom in a 1+1 CFT to a 2+1 ADS anti-de Sitter space curved space. And in principle, this construction we have is extendable to higher dimensions using a higher dimensional Mera construction. The whole bulk state is also constructible by a log depth quantum circuit. So this is something that could be tested in the quantum simulation. And we have another follow-up paper describing, coming out soon, which will describe how one could do this using a network of bosons. Several features of the holographic duality are observable. Relation between boundary entropy and bulk length as measured by a bulk phenomenon entropy. this gauging of boundary symmetries in the bulk and the existence of holographic screens. And some things we're interested in looking at is it possible to use this construction to probe the topological quantum field theory CFT correspondence, where you'd have like a two-dimensional topological quantum field theory with a boundary CFT. It turns out we found a construction which does so for a boundary theory with a Z2 symmetry, but the tensors in the network are not all isometries, so it doesn't fit nicely into our scheme. And then the other thing would be very interesting to look at is the dynamics of excitations. So let's say you make some excitations in your bulk. How do those interact? And this is something we've started to look at, because you can write down a parent Hamiltonian for the bulk, but it's open research. Okay, thanks a lot.
All right. So thank you, Gavin. Are there any questions? Feel free to type them or raise your hand. Give people a minute.
May I?
Well, yeah, go ahead, Akin.
And given towards the end, you spoke about the Renyi 2 entropy.
Yes.
Why the Renyi 2 entropy? Wouldn't you have preferred to do it for the Renyi 1 entropy?
Oh yeah. So yeah, although there's a version of the Ryo-Taganaki formula also for the Renyi 2 entropy, and it turns out that that's a much easier thing to calculate with our tensor network.
Sure, but when you have the scaling of the 2 entropy, what can you tell about the scaling of the 1 entropy?
Oh, it's a similar relationship. So it will grow linearly with the central charge and logarithmically with the size. It's just you get some additional prefactor that's different.
Okay.
So any other questions? I've got one. So tell me about the continuum limit, or tell me whether you can tell me anything about the continuum limit of such a model.
Yes. Just outside of tensor networks, we've been trying to understand the continuum limits of CFTs using other techniques, in particular using wavelets. So yeah, I mean, there are these peculiarities that arise. So for example, the entanglement entropy you get even from just a 1D system depends upon the cutoff length of your lattice, and it diverges with that. And so it'd be nice to have a concrete understanding of how it diverges. And you find you can show with using a wavelet construction, which guarantees orthonormality as you increase the resolution by factors of 2, is that it does indeed grow with the resolution of your description. So for every doubling of the number of degrees of freedom, you get the corresponding increase in the entanglement entropy of a region. But there's some other subtleties, like how do you properly represent the conformal data with a lattice model? And when you try to do it with a tensor network, one of the problems that arises is that your tensor network might not satisfy translational invariance. So there are some approaches to try to correct this. So Suki's been looking at some approaches using Frobenius algebras. But another approach is maybe taking some ideas from band-limited theory and saying, well, maybe it doesn't matter so much, but maybe your underlying description of the tensor network might not be translationally invariant, but maybe there's a when you compute observables, you take appropriately weighted computations which account for the fact that you have this band limit. So yeah, it's something I would like to certainly understand better.
Well, we should talk about it. That sounds really interesting.
Yeah, absolutely. I think, yeah, what you could get is a smooth connection between the discrete and the continuous, but the price you pay is that the what used to be nearest neighbor interactions only will stretch much further.
Yeah, that's right.
Yeah.
Okay, we've got a couple more minutes. If there's any more questions, I'll give people a sec. You can't just survey the room and see if anyone, if everyone's going like this, then you're done. But you can't do that here. Or if everyone's like getting up and ready to go.
I did find that there's a way to get a laugh track working in Zoom, but didn't have time to say.
Oh, nice. Oh man,
exactly. I was just about to suggest, Nick, you should have that. An applause.
Yeah. We need a like a standby music, some elevator music or something, like when there's technical difficulties.
You can record yourself, Nick, and play.
I suppose I could. Yes. I was at a conference where Steve Flamia did that once. He just put it on his phone and just put that on the microphone when they were having technical difficulties. It was pretty good. But yeah, I don't have that teed up.
And
all right, are there any other questions?
You see, and a smooth voice would say, your Zoom call is very important to us.
Yeah, that's right. All right. Well, if there's no other questions, I think
I have a question, Nick.
Edu has a question. Go, Edu.
Why are there two Fabio Costas in the? I'm saying two. I'm not dreaming this, right?
You're not dreaming this. There's also two of me.
Oh wow. Okay.
That. Yeah.
One is a computer and one is an iPad.
I see. That explains it.
Yeah. Great. Well, if there aren't any other substantive questions for the speaker, then why don't we thank all the speakers of the session and all of the speakers in all of the Aussie sessions, because there were many. So let's all do our virtual clap. Excellent. I'll do my real clap. Yeah, well, thanks to the Waterloo folks for doing the bulk of the organizing for this conference, and thanks to them for working with us to have some Aussie sessions. I think they went really well, and it's a great opportunity to connect the two communities and maintain the connection despite the time zone difference, which is acutely felt when you can't travel.
I can paste here if you want, Nick, the link to the playlist where both the Waterloo and the Aussie sessions are being uploaded.
That's absolutely, go for it.
It's now in the chat. So that's a YouTube list with all the sessions so far, except for this
fantastic.
one.
Yeah, fantastic. So everyone copy that. And I presume you'll send it out by email at some point too.
Rick usually sends it in the reminders.
Nick, let's remember also, it's not just the two communities in Australia and Canada, right? I mean, this is meant to be for everybody.
Yeah, absolutely. But I just mean that we're spanning a large portion of the time zone here. If we had one in Europe, then that would be the remaining one. But yeah, it's been very good. Okay. Yeah, I miss having the in-person meeting as well. All right, all. Well, I think I'm going to stop the recording now and sign off. Thanks.
Thanks.
Thank you. Oh, let's thank Nick because the recording finishes, because he's been chairing this session. Also Tim, but Tim is not here.
The recording has not finished yet. Thanks all.